Ξεκινήστε, πείτε μια περίληψη στα πρώτα και συνεχίστε.
Okay, so I'll start again. So I will skip the philosophy and I will present the transparencies as fast as I can. The model that I will present is a non-local model. And this will generalize basic law of physics and materials. One of these laws is Hooke's law, another for continuous media, elasticity, another very well known is Newton's law. So I will concentrate on showing how these laws can be generalized to include non-local action. And the basis of it is one observation of Maxwell, who stated and showed that the average value in an elementary sphere and the value of this variable, the value of a variable, the average value of a variable in an elementary sphere, and its value at the center relates with the Laplacian. So he gave the first physical meaning of the Laplacian. And the whole presentation will be based on that. So we go back to giants of science like Hooke, like Newton, and Maxwell. And revisiting their ideas, we can cast, I will show you, we can cast new relations that will give us new directions to work on and apply the new tools that some of them were presented, for example, today. So the motivation for this was my original work I did with a mathematician, a reasons professor in Minnesota at the time, Jim Sherin, very, very distinguished mathematician who proved, for example, that Carathéodory was wrong in two places in the proof of the existence of entropy, just to show you the caliber of the man. And we did a very simple problem. We looked at an interface, a liquid-vapor interface. This problem was looked first by van der Waals in his PhD thesis because of this equation of state, the non-convex equation of state, of pressure versus density, which in the negative slope regime is unstable, there is an instability, and the material cannot survive in this regime. It splits in two phases, the liquid and the vapor. And Maxwell also, using classical thermodynamics arguments, which do not apply in these cases of highly unstable processes, show that the equilibrium pressure in this interface, you see a vapor-liquid interface. The pressure is constant in both phases. And the densities of the vapor is ρ1, and the density of the liquid is ρ2. He showed that the three numbers of this phase transition are relayed through Maxwell's rule, which is the second equation in the slide. So what we did with Sherin, we looked at this new idea of the interface not being just a line, but being a continuous medium. So you can become very small and look at the interface as a material, as a continuum. And instead of having a sharp interface, so it was the first work to look at the nanoscale problems. And instead of having an abrupt reduction of the density from ρ1 to ρ2, you have a smooth one. So within the interface, the density is continuous, goes from the value, the high value of the liquid ρ2 to the value of the vapor ρ1 through this smooth transition. And this is a concept that is used also in phase transition theory today. So what we did with Sherin was to abandon the structure of classical thermodynamics that was used by Maxwell, make an economy of acids, And this is only the principle of momentum or equilibrium for this case. That the divergence of the stress is zero, is the first equation in this line. And then you have also to make what we do in mechanics, a constitutive equation for the stress. And instead of having that the stress is P of rho, which is a function of the density only, which is non-convex, which is the diagram there shows van der Waals equation of state. We assume because of this transition of the density from ρ1 to ρ2, the high gradients involved in the interface, the stress depends on higher orders gradients of, this is the most general constitutive assumption you can write, where the Laplacian appears there and also the first gradient, the absolute value of the first gradient, and some other terms. It doesn't matter. Now, this is the most general expression you can write. And then you can apply this to one dimension, because you look at one-dimensional interfaces. And what you can show, just from the solution of the differential equation, that I will show you in the next slide, you can show that Maxwell rule is violated and is replaced through the last equation, the Maxwell rule modification. The 1 over rho squared term is replaced by E of rho, which is shown by this expression, where B and A are this, they relate to alpha, beta, gamma, delta. So the interface and the transition depends on the structure of the interface. Okay, we show this. Okay, so this is because one of our colleagues presented differential equations which were not partial but ODEs. This is the case if you consider steady state or equilibrium that you have an ODE. And the ODE you have to solve is this equation, first, second, third equation, with A and B being the sum of alpha plus gamma and beta plus delta. So you have to solve this equation, it's a nonlinear equation, and the interesting feature is that P of rho is non-convex. It has a negative slope regime. And the solution, for existence of solutions of these equations, is very simple. I did that with Sennenherz. Okay, I should not say history, but you can prove now that in order solutions to exist, the pressures at infinity, minus infinity and plus infinity, which is, must be the same. So P over 1, P over 2 is P. And the analytic solution is given by the last expression, and Maxwell's rule is replaced by the second equation here, by this equation, where E of rho is like that. Now, we applied this with physical chemists in Minnesota to practical problems, to calculate interfacial tension. I will not show you details, but we calculated, or they calculated, they were experts in this, surface tensions for many liquid phases, not for water, but for other materials as well. And this was a work that motivated the rest of it. This was in 1983. But this motivated what is called now gradient elasticity and gradient plasticity, which you can find more than 6,000 references to each of these topics, because many other people in continuum mechanics work along these lines. So I will try to be brief, just to give ideas rather than details, that this was applied, this to solid interfaces. And you see the basic equation, you have like two films from different materials. They are adhered to each other with an interface. And if you apply a stress, the strain in one film, depending on its material constants, is gamma 1, on the other is gamma 2. And it looks like there is a discontinuity of strain between the interface. But this discontinuity is eliminated through the Laplacian there, and you can obtain solutions for the distribution of strain, as well as this. If you like to look at the interface as if you like to homogenize somehow and say the interface is like a line, then the modulus of the interface is given by the particular moduli of the two phases that are in contact, plus these coefficients, the gradient coefficients, we call them, or internal edge. This I skipped this slide, is the solution of the differential equation of the previous solution. You can have three types of solution. You can have transitions, you can have reversals, we call the second part, which is like bubbles in a liquid or liquid in a gas, and you have periodic solutions. These were not known to van der Waals. So again, simple mathematical work reveals this, which motivated the second part, the reversals motivated what we call now shear bands in plasticity. They gave a measure of the width of the shear band and the spacing of the shear band. Shear bands is like when you take a plastic and you stretch it, you have these lines, you see, that the deformation localizes. So it's a beginning of pattern formation, sort of, for deformation problems. Pattern formation was looked at the chemical systems initially, but this approach, the Laplacian approach, generated a lot of work on pattern formation in solids for defects as well as for this localized type of deformation. And this is what we call now gradient plasticity. It's used to address this type of pattern formation. So I think I skip that. What? Okay, so I like to show you the generality of the approach. The first equation is Hooke's law. The stress relates to the strain with elastic constants, which is the constant in shear and the constant in tension. So these are sort of lambda g. This is Hooke's law. Now, if you say that the strain, in this macroscopic law, the strain is an integral of the strains in the neighborhood. So you have an integral expression for the strain that comes in Hooke's law in terms of the local strains around this point. Then you can show that that the strain in Hooke's law is replaced by the local strain and the Laplacian, by Taylor's expansion and certain arguments. So Hooke's law then, by just replacing epsilon with its counterpart, which is the second equation with the red term, you obtain this third equation, which is what we call now gradient elasticity. So you see, it's very simple form. It's Hooke's law and the Laplacian of the macroscopic stress as a second term. Now, I will not go to plasticity, but the same recipe can be applied to plasticity for what we call, you don't know, you don't have to know that, equivalent stress and equivalent strain in plastic flow. So the usual law, which is the third, which is this equation here, the usual law, the black terms of the stress, of the equivalent stress related to equivalent strain like that, is modified again by the Laplacian. And the same is done, or can be done, for example, in Fick's law or Fourier's law. Now, J is the mass flux, grad rho is the concentration, the gradient of concentration. And the same law writes Fourier for the heat flow. Q instead of J, and gradient of temperature instead of concentration. And if you say that again, you replace the macroscopic quantity J by its microscopic counterpart, then J is replaced with this. Again, the Laplacian of flux. And if you use this with a mass balance equation, which is this, then you obtain a fourth order equation. You see, it's important that I emphasize this here, because in 68, Kahn and Hilliard in phase transition, I mean, when you have a uniform concentration of copper atoms, say nickel, and you squeeze, you put the temperature low, you cool it very suddenly to a certain temperature regime, then instead of having diffusion, which is from regions of high concentration to regions of low concentration, mass flows opposite. From regions of low concentration, you go to regions of high concentration, as for example happens to societies. People leave the villages and go to big cities. Okay, there are analogies with transfer uh, of energy, of heat, of mass, of population as well. And so this is the unification of science anyway, through differential equations. The diffusion coefficient, people thought that the diffusion coefficient is negative, but it's impossible to have negative diffusion coefficient because you have instability. You cannot do anything mathematically. So the importance is the last term, the red term, which you can have D negative, but C is positive, and the behavior of the system is stable. And you can obtain patterns. You can start from a uniform concentration, and then you can come with batches of nickel. So it's the beginning of a new phase transformation. So I have shown you three models where classical laws are are generalized through the Laplacian. And this is easy to follow and do things because Laplacian is very well known in mathematics. And not only that, but this has been extended to fractional calculus as well. Again, in Laplacian, the fractional Laplacian is well treated. So there is a lot of new directions that come out now, and many new techniques that were applied to classical equations can be transferred here at C in an easy way, sort of, in a classical way. You can see what new things you can obtain in relation also with new experimental observations at the nanoscale and the new tools you have to observe patterning and other phenomena. The classical equations were developed when you have simple tools. You have to not so sophisticated. You have now to go down to the subatomic level that physicists do. Okay, so I spent time just to give you an introduction of the ideas, and because it would be useless to write many equations. I like also to say that why this simple law of Hooke generalization, which I call it Gradella gradient elasticity, is giving easy results. You can, if you combine this new constitutive law with the divergence of sigma equals to 0, which is the equilibrium equation, then you can obtain solutions of gradient elasticity through solutions of usual elasticity, of classical elasticity, through this equation, which is called now, it was basically discovered by Roux, who is a famous professor in Canada, and was my postdoc in Michigan many years ago. He came from China. Excellent talents he came. Now Chinese do their work at home. So if I know solutions of classical elasticity, which many books have written on that, then I can obtain solutions of gradient elasticity with this non-homogeneous Helmholtz equation. You see the first equation for the displacement and for the strain. And one very remarkable result that was just, I like to show you this, for that is to show how singularities are eliminated, classical singularities, in dislocation lines at crack tips. Many books have been written in cracks, in the fracture, and the solutions are singular. When you go near to the crack, the stress goes to infinity. And the same thing happens for dislocations. So I show here the example. You see how beautiful, simple formulas you have. The black terms, the first term here, is the classical solution for what we call elasticity solution, what we call edge dislocation. You see the singularity is y over r squared for the stress and for the strain as well. And by doing the Roux theorem, I said, the Roux Aifantis as people call it, then you can obtain easy solution in terms of Bessel functions. And you have this parameter C. And by letting R to go to 0 in the dislocation line, this second term becomes exactly y over R squared, and the singularity is eliminated. So you can, at small scale problems, when you have to worry for the stress in very near dislocation or crash, now you have a mechanism to do that. And there have been written many papers on this thing. Mathematical work was simple, was not difficult at all because of the Laplacian, the Helmholtz equation, which is known. Okay, so let me move now to what is most interesting. And okay, these are more things. We saw the elimination of singularity from cracks with this exponential term, but and also I like to show you this from example from Murray. Murray is a famous uh, mathematical biologist. I like to show he wrote extremely good books, and then I, I discussed with him about 2 years ago. I will say what we discussed. Here is an example how the cells crawl through the matrix, the extracellular matrix. They have small legs and big legs. The small legs is for when they move, they crawl according to the fixed law, as you will see. And the long legs are the non-local effect, which move according to the fourth order term that I showed you in the first slide. Now, what Murray did, he did bifurcation and pattern formation theories for the orders, even for the orders. No, so he revisited Turing's theorem of chemical patterns by adding one more equation. And this one more equation was the elasticity equation, which is which raises by the interaction of cells as they try to crawl through the matrix, through the extracellular matrix. This was not being accounted because Turing, in his famous papers, which was rejected for 3, 4, 5 times until it was accepted, because it was violating classical thermodynamics, because he was showing the formation of patterns, chemical patterns, which were observed. And the tendency of classical thermodynamics was to write an entropy which spreads things out, uniformity, while he was showing structure out of uniformity. Okay, so Murray then wrote equations. I'll just show a couple for these processes. So you see, for the cell dispersal, there is the fixed law, which is the proportionality to the concentration of cells, and he added this extra term for the big legs, which is the Cahn-Hilliard type. It generates the fourth order term. So this is for diffusion, for how, but for the interaction of cells with the extracellular matrix, look what he proposed. Exactly the same equation that I showed you for elasticity that we were doing for metals. And so again, we see some the compatibility of ideas somehow when you like to take into account, no? And also by Gall, who was a mathematician, was not a mechanician. For me, it was much easier to do that because I grew up with Hooke's law and its modification. Why also you need modification because in small scales there are the so-called size effects. In other words, you do an experiment in big scale and the experiment in small scale and observe different results. And if you include the Laplacian, then you can the results are the same. Okay, so you have a unifying theorem to talk about the big and the small. And the connection in this at least approach is the Laplacian. So I'm telling you simple things because I grew up as a material scientist. I became a sort of a mathematician in Minnesota where I went to with people like Amundsen and Eris who were responsible for the for most chairmen in chemical engineering departments were their students. And for 40 years was the best department in the world. So this is luck. And that year the Department of Material Science joined with chemical engineer, and more or less I brought ideas in chemical engineering pattern formation to metals. Because in metals also there are like generalized chemical reactions. Those dislocations that I showed you before, they can annihilate to form perfect lattice, or they can get together to form patterns of dislocations. And these patterns, I work with people in Brussels, the precogenic group, and he has this self-organization approach to dislocations in his book with Nicholas. New things, new ideas. And some many new ideas were generated here. Maybe they were not expressed very openly, but I see that there are possibilities for new things to be done. For example, stochastic terms were not added anywhere. Stochasticity. You can obtain, you can add stochasticity to your bifurcation thing at C. Yeah. Anyway, so I like to finish because I don't know how much time. Yeah, okay. This is something I told you that at the beginning new ideas are not accepted very well. So this gradient plasticity was in 84, and it was not until 10 years later when Fleck and Hutchinson wrote a variance of this theory, of the 84 theory of gradient plasticity with a Laplacian. They wrote a very complicated, more complicated theory that the work was recognized very much. And the 6,000 papers I told you, they are on both theories. Some people use my original version, some others use the Fleck-Hutchinson version. Fleck is in Cambridge, Hutchinson is in Harvard. And I owe to them that they brought this work to the surface. Now, what was though of interest and very funny is that another continuum mechanics person, Gertin, who is a guru in continuum mechanics, a mathematician, in Brown and later in Carnegie Mellon, and Anand, a material scientist with excellent background in mechanics in MIT, they wrote an article that they said that the model of Fleck and Hutchinson is not compatible with thermodynamics. While the original one that I showed you with the Laplacian is compatible with the continuum thermodynamics. Okay, I will not comment on that because continuum thermodynamics is not like a holy grail. You can, you can modify it to accommodate Fleck and Hutchinson as well. But the other theory, the Laplacian theory, is much simpler. It's so nicer and so more convenient to use. So I'm getting away. So the last thing that I like to show is the modification of Newton's law. We know that Newton's law is F over R squared. Okay, this is, the other are the constant. The R is the direction of the force. So if instead of that, and I will not discuss the basis of it, if instead of F equal the classical F, you introduce the Laplacian, in radial coordinates, this is the equation you can solve, and the solution you obtain is this one for the force with the distance. There is an extra term here. The classical term, A over R squared, and an exponential term here, which comes from the Laplacian. Now, when R goes R goes to infinity first, when the two bodies that they interact are far away, you have the classical Newton's law. But when the bodies are close together, you cannot get rid of a new parameter, the force parameter beta, which is it becomes AB over R squared. Only that I like to say, that by adjusting the parameter of B, you can make the force very large, and this is what we claim here that happens within the nucleus when the subatomic processes, at least when masses are very close to each other within the nucleus, as I said, the matter is held together. And there are four kinds of forces in physicists say. There is the gravitational force, Newton's type. There is the gravitational force is very weak compared to the electromagnetic force and compared to the strong force. And this is just a simple way by modifying the classical law that you can make beta very large, so you can make the gravitational force equivalent sort of in value to what people use physicists as a strong force. This is completely simple and completely new and could be completely wrong. That's the question. Why? There is a group of physicists 20 years ago, Fishbaugh in the United States, New Jersey, who proposed the fifth force. They did experiments in tunnels, very 2,000 kilometers down the Earth, and they found that they deviate from Newton's law. And uh, later, about a year later, after we proposed and published something on the modification I show you, I found his papers, which proposes an equation like that, exactly the same form, exactly empirically. And beta and L are big. They are distances of geological 200 meters for correcting the experiments interpreted on Newton's law. Okay, they did that. And this was remarkable for us, of course, for everyone. But then, they wrote about 5, 6 years ago. He wrote a book, "The Rise and the Fall of the Fifth Force." In other words, when they worked as a group, they found out that the experiments, the measurements that they did were not correct. They had a mistake. So Newton's law was not violated. So number one. Number two, in physics now there is also one Greek guy, but many more who work on many dimensions for elementary particles, fifth or seventh dimensions, and they write equations for these interaction forces in high dimensional space. And when this is very remarkable, when you project these expressions into three-dimensional space, you find an equation very similar to this one that I show you, which is produced by Newton's modification. Now, I don't think you would like to spend time, and it's not, there are a lot of symbols here. This internal length L and the beta parameters for the force within the nucleus have to be interpreted in terms of this new, I mean, the physicists, the physicists quantities. M naught here for H is the Planck constant. M gamma is the one, this what we call the relativistic parameter, 1 minus v square over c square, where c is the speed of light. G is the gravitational, the gravity. MP, the gravitational constant. MP is the proton mass. M naught is the neutrino mass. So this work was done with my colleague from Patras, actually. My classmate was in Polytechnic School, chemical engineer. Vagenas is his name. The Greeks know him well. He's also an excellent teacher. And the motivation for these constants like that were obtained from, as I said, joint work with him without using Newton's modification, but using what he calls a three neutrino model, moving like Bohr's model. And it doesn't matter now, but it gives you these physical considerations, even with this simple model, gives you the motivation to adjust the constants beta and L into the modified Newton's law. And when you do that, and you use this, you find out that this F that I show you, by adjusting beta and L, this F turns out to be 7 10 to the 4th Newton, which is the strong force which is estimated somehow, if my statement is rough but not incorrect, with the standard model of physics, which is very complicated. I do not understand. Most of us do not understand. It is in high dimensional space. So the question is, can simple things that were done for the three-dimensional space we were, without using relativity, and concepts from special relativity as used, like the speed of light, concepts from quantum mechanics, like the Planck constant, but they are put together in an engineering type way, in an engineering science way. Did I finish? Did I take more time? Where I am? Do I have time or finished?
Professor Aifantis, for you, we don't have limits.
You have limits.
For you, no. You can speak unlimited.
No, I will not speak unlimited, but I like to. You see, all those things happen through the interaction. I had extremely good co-workers and extremely good students. Not everyone, but some of them. And I think even now at my stage, that I don't know how long I will be around, being thinking, it's very important that we get together with different fields and put the strengths, each one, have different strengths. And then new things can happen. My work would not have been like that without, for example, Serin, without Zbib. Zbib was my very good student who died early. He was chairman in Washington State. He had a car accident. Without Baman, another student. And also, I've mentioned Valgraf, a student of Prigogine, that we did this deformation patterning. Ashkes is chairman now also. Yeah, they grew up. But they worked with me as docs or postdocs, and they knew more, much more than I did in this particular area that we were working technically. And they applied the tools with the ideas from a different field, and the new things were generated. And I'm still curious to follow up. Now, what I will tell you with this concluding slide, it is the computational that people do. Sorry, people do on computational material science. They do molecular dynamics, and the only correct potential that is derived from quantum mechanics is this one, is the London potential, which has 1 over R6 singularity and accounts only for the attractive part of two atoms being together. But as you know, the atoms are coming together and then they stop at an equilibrium state. And if they come closer, there is an opposite force, not the repelling force. The repelling. And this, when I was reading, just because Feynman is excellent books in physics. He said that if an extraterrestrial comes and discusses our advances, he will be surprised why atoms come together and then they stop. They form mass. They form the world. And he said that there is this 1 over R6, the London's potential, which was derived from quantum mechanical principles, but has only an attractive branch, not a repulsive one. And then people, because they were doing it, and there is this repulsive from physics, they were modifying this R over 6, you see, the minus R over the famous Lennard-Jones potential, the R over 6 term, adding empirically an B over R12 in order to obtain both an attractive and a repulsive branch with equilibrium R naught here for both the force and the potential. So that's how it was done, and many potentials were developed and so on. So the question that was raised a couple of years ago was, can gradients do something for it? Okay, so if instead, again, the same trick, the same coffee maker, if instead of the classical equation, the classical form, phi naught, which is like C over R6, as you see, you add the Laplacian, there are reasons, a non-local effect. Then the solution is a little complicated, but you obtain both a repulsive and an attractive branch. At least on theoretical basis, this is very pleasing because it shows that you cannot, even at the quantum level, non-local effects are important. I'm not talking about these fancy things that quantum mechanicians do because I don't know anything about them, but they have this thing about this non-local interaction. This is weak non-local interaction through the Laplacian only, not this very far non-local interaction. And I just like to show this that at least for argon, is this for argon? Do I say argon somewhere? Yeah. For argon, I show you the results of London, of Lennard-Jones, which is the red line, the London, which has, you see, the London has only this, no branch, no repulsive branch. It breaks down here. And also the gradient I show you, which was done adjusting the constants to reproduce Lennard-Jones. Now there are so many potentials, and so you can see if the gradient, if the Laplacian can do something for you, and then use the applications. Now the final thing is that this method, the Laplacian method, can be extended to fluid mechanics. So the dark terms here is Navier's equation, the stress and the symmetric part of the velocity gradient. You see this is Navier's equation. And then all fluid mechanics are based on the Navier-Stokes equation, which is by taking this and putting this into the momentum equation. Instead of having divergence of the stress equals 0, you have rho v dot. V dot is the velocity. So there is, yeah. And this is the the Navier-Stokes equations, the black terms. You see the black terms. And this fluid mechanics is based like that, like elasticity theory is based on Hooke's law. So if you follow this Laplacian thing, you have this extra term, and anyway, and this is not, people, like I mentioned Gerting before, try to do similar things for turbulence, and in the rheology, people like that, you see this is Lamé, the Navier-Stokes form, the black, and the added term sigma, the stress, which this is the called diffusive Johnson-Segelman model, which you see it doesn't matter. It has this the Laplacian evolution. Okay, but the last is that I talked to you about Maxwell. Maxwell equations can be also just replaced by this new red term here, and also the quantum mechanics equations. This is okay. I think this is in a famous book by Davis, which he produces this for the wave function. Okay, this wave function, and the proposal is to replace the strain at the quantum level instead of writing epsilon with this thing as you did for Hooke's law. So there is a recipe, and I think I finished. There is a recipe. I show you a lot of perhaps equations, but they are all more or less the same. A recipe with classical sort of tools because it's PDEs. Of course, you can replace this with fractional at fractals, and the Laplacian is well suited to it. But there are so many techniques now, like control theory, to optimize the strength of a material. There are these lectures that we had in the morning for bifurcation, I think. And so instead of looking to the classical equations, can we just use these tools? If there is enough evidence that these equations are more useful for the nanoscale, for example, new tools to try to see what will happen and educate younger people who can follow up. And also apply, as you said, to the social systems. Non-local effects has not been used in ecology. Non-local effects has not been used also in biology, in biomechanics. And it's straightforward because biomechanics, ecology, they were motivated by reaction diffusion systems. These are higher order reaction diffusion systems. Okay, that's finished. Okay, thank you for inviting me in a small conference which has nice ideas.
Then if